Hey guys, welcome to Unit 1B, Notes A. Now we're going to start at Chapter 1 in the beginning of our book, and we'll name this Unit 1B because we did a little blurb from the Chapter 11 with 1A. In Unit 1 Notes A, Unit 1B Notes A, we're going to focus on phases of matter. In particular, we are going to use some concepts that we're familiar with in order to go into some detail of explaining why the phase diagram or heating curve looks the way that it does. Why are there plateaus? Why is one plateau longer than the other? What do the particles look like at every section of this graph? So the familiar concepts that we're going to use to explain these things are two things. One, kinetic molecular theory, which if you remember had three postulates to explain particle motion. Then we're also going to look at intermolecular forces and the strength of intermolecular forces, the properties they cause, and how that plays a role in this phase diagram as well. And then we'll finally get to the diagram itself and see it all come together. So let's first start with a little review of kinetic molecular theory, or a theory, an explanation that explains the movement, the kinetics of molecules. So the very first postulate is that all matter is made of particles. Those particles are always in motion. Even a solid, which doesn't seem to be moving. This board isn't running circles around me, it's just sitting here. But if I got down to a particle level, you would see a vibration. So all matter consists of those particles, not waves, always in motion, not still. The second postulate says that as you increase the temperature, or as you add heat energy to a substance, you're going to increase the movement of those particles. So I've always used a shorthand that says if I increase temperature, that's going to translate to an increased kinetic energy. It's a law of conservation of energy application as well. Adding more heat energy can then be converted into adding more kinetic energy. So it's going to give the energy to the particles in order to allow them to move faster. And we can actually now apply some physics to this in order to see how the particles are going to actually engage with each other. So if I have more kinetic energy, the formula for kinetic energy, if you haven't taken physics, you will see, is proportional to a velocity. So the formula for kinetic energy, Ke equals 1/2 mv squared, where v would be the velocity or the speed. Velocity is just speed in a given direction, so the speed of the particles. So when we say things have more kinetic energy, when we connect in what that means in terms of physics, we also can start explaining how the speed is exponentially increasing as we have more kinetic energy, and then tie that back to how the kinetic energy came from the increased heat energy or the temperature. So it's kind of interesting with IB, you're going to start to see some crossover in not just chemistry, but also involving some physics as well. So if you haven't taken physics yet, you're going to be able to see kind of a little insight of how things work. If you are taking physics right now or have already taken it, you're going to have a lot of really cool aha moments throughout IB. All right, enough of a little side tangent. Let's look at the third postulate down here, in that if I have an increased mass, then I would have decreased speed, more of an inverse relationship. Increased mass would be a decreased speed. Less energy in the particles, they're moving slower if they have a greater mass. Whereas if you have an increased temperature, they move faster. So direct proportion versus an inverse proportion. So these are some explanations about how particles move based on the properties and the energy of the substances. The next thing I want to look at is a little review on intermolecular forces. All right. So if I look at intermolecular forces, you may remember that that's different than intramolecular forces. If I have a water molecule, hydrogen attached to oxygen, that molecule is held together by a covalent bond. That would be an intramolecular force, the covalent bond inside. But if I have two separate water molecules, remember water is polar, so we would have a partial negative and a partial positive. that attraction between the two particles would be an inter or exterior molecular force. So when I'm looking at the strength and effects of intermolecular forces, I'm thinking about the interaction between two separate molecules in a substance. For example, a bucket of water, I'm looking at all the different particles interacting with each other, all the different H2Os. So intermolecular forces depend on what they're made of. The basic idea is that the greater the difference in either electronegativity or charge, the greater the difference in charge in general, the stronger the intermolecular forces. The other thing that plays a big role is how close together the particles are. What kind of particles have the closest together, what kind of substance would have the closest together particles? That would be your solids, where they're fixed in place. And then, according to kinetic molecular theory, as those particles gain energy, they would move faster. So substances at higher temperatures, for example gases, would have the weakest intermolecular forces because they are the furthest apart. So gases would have the weakest intermolecular forces, solids the strongest, with of course liquids being somewhere in between. So there are three main types of intermolecular forces that I want to review right now. The first is the strongest of the intermolecular forces, and that's because it's looking at ionic bonds, which have complete full charges. The charges come from periodic table or things to know and love. For example, sodium we know is in the alkali metal group, so that would have a +1 charge. Fluorine as a halogen would have a -1 charge. And every atom has its own unique charge. Calcium +2, oxygen -2. I'm just going to go ahead and fill these in. So every atom has its own charge. The strength of the intermolecular forces between the ion and ion interacting with each other, ion-ion interaction, is based on how far apart those charges are. Think of it as a number line. If I were to go from +1 to -1, +1 to 0 to -1, that's a difference of 2. Whereas going from +2 to -2 would be a difference of 4. And going from +2 to -1 would be a difference of 3. I'm only interested in the difference between one ion and one other ion. Remember, these are actually intermolecular forces. So let's say I have calcium and 2 fluorines. It's the interaction between a single fluorine and a single calcium that I'm trying to look at the strength of. So I'm going to ignore the subscripts. I'm just going to be looking at the difference in charges. Now, in an ion-ion interaction, the greater the difference in charge, the stronger the bond. Now, the stronger the bond, the more energy would be required to break that bond, which is going to lead to higher melting points and boiling points. And that's an important connection. So I want to kind of make note of that on the bottom of the screen here. If I have an increased difference in charge, that means I have increased strength, which means more energy to break the bond, which means higher melting point and boiling point. So the more different it is, the more tightly it'll be held together, the more energy it would take to break it up. And then that's going to lead to the higher melting and boiling points. So of my 3 compounds here, the highest melting and boiling points would come from the difference of 4. So CaO would have my largest melting point or boiling point. The lowest one here would be NaF with only a difference of 2. And then CaF2 would be in the middle with a difference of just 3. So we can look at the strength based on the difference in charge. We can also apply this concept to covalent compounds. But in the same way that an ionic charge is a full charge, that being a bigger difference, making ion-ion interaction stronger, a dipole-dipole or polar molecule versus a polar molecule is going to be less strong, less of a difference. So ion is strongest, and we can look at the strength within them, like we just talked about with the difference in charge. If I have a polar molecule, that's going to be less strong because there are only partial charges. So remember, a dipole is the name of a polar molecule. So this would be an interaction between two polar molecules. For example, this chlorine's partial charge being attracted to this hydrogen's partial charge. So whenever that happens, we call that a dipole-dipole interaction. There would be an attraction between those two separate molecules. If you had non-polar molecules, you would not, excuse me, have a dipole-dipole interaction. Now, the greater the difference in these partial charges, the stronger this type of interaction would be. So there's actually a special type of bond dealing with the most electronegative elements on the periodic table and the most electropositive atom that can form a covalent bond, which is hydrogen. So we call that hydrogen bonding. And that's going to be whenever you have hydrogen and oxygen, nitrogen, or fluorine, the most electronegative and very, very high, very similarly high electronegative atoms. Because what that means is this partial negative is way more negative than any other type of dipole. And then this hydrogen, much more positive than other types of dipoles. So we have a great difference in charge. And as we talked about before, whenever you have a big difference in charge, you're going to have an increased strength here. So hydrogen bonding is actually the strongest type of dipole-dipole interaction. But it's so special, we highlight it as one of the main 3 types of intermolecular attractions. Now, whenever you have really strong interactions, you're going to have special properties. So there are 3 main properties that you should know for things that have strong intermolecular forces, such as water with the hydrogen bonding. So the first is surface tension. Perhaps you've seen a bug walk on water. You may have tried to float a paperclip on water. Now, paperclip's made of metal, it's supposed to sink, but you can make it float temporarily, being very careful not to break the surface tension. What happens is those interactions between the water molecules create almost like a net on top of the water. And that can actually support a little bit more weight than it normally would. So it can have that paperclip floating on water. Surface tension is where the water molecules attach to each other like a net and can support something else. Then there's 2 other types of properties, but they're related to each other. So we have cohesion and adhesion. Cohesion is basically the substance liking itself. Perhaps you filled a cup of water up over the top. It's able to rise above and almost defy gravity because the water molecules are attracted to each other. So anytime you see that bubbling, maybe trying to collect a bunch of water on top of a penny, bubbling over the cup, that's going to be an example where cohesive forces are dominant. You can also have water attracted to something else. For example, when you read a graduated cylinder, we read from the meniscus. Well, why does the meniscus even exist? The water molecules are trying to climb up the glass of the graduated cylinder. Water is attracted to the graduated cylinder, actually more than water is attracted to itself. So whenever that happens, you have the meniscus we're used to. But some substances, this example here is mercury, actually do have stronger cohesive forces than adhesive forces, and you almost get an inverted meniscus at this point, where it would bubble as opposed to climbing the wall. So cohesion, water attracted to itself, or adhesion might be water attracted to something else like glass. Cohesion and adhesion, both a result of interactions between molecules or intermolecular attractions. So now let's put this together and look at how the kinetic molecular theory and the intermolecular forces affect the shape of the heating curve. So the curve essentially takes water, or H2O, which is less than 0. So we're going to have to heat it up to 0 to get the melting. Then we're going to heat up the water to get vaporization. And then we're going to heat up the gas. And we're going to look at what that graph looks like over time. Now, this is a little pet peeve of mine. A lot of textbooks plot this graph against time. But really, in order for this graph to happen, we have to be applying heat over that time. And the true independent variable would be the heat. How is the heat affecting the temperature? So you'll see both in the note takers, but time is what you'll see in the textbook. And the reality is you must be applying heat in order to get this graph. All right, so the first thing I want to point out about the graph, something that we didn't really talk about in honors, is there's actually a difference in the length of the phase changes. So the melting plateau is much shorter than the vaporization plateau, where you would have boiling or evaporation. You should know the temperatures for water. The melting always occurs 0 degrees Celsius, and vaporization always at 100 degrees Celsius. Those are where the plateaus go. So let's take a look at what the particles look like as we go through this progression. When we start off with the -20 or negative whatever below 0, the solid, think ice, those particles are very close together. And according to kinetic molecular theory, they would be vibrating even though they're stuck in place. They would be moving. So as I add heat energy or apply heat over time, the temperature will increase. Remember that temperature is the average kinetic energy. That is the definition for temperature, average kinetic energy. So according to KMT, adding heat energy will increase the kinetic energy, and so you should see an increase in temperature. Once you get to the melting point, that substance will start to melt. And so you're going to see the particles start to move further apart. Not as far apart as with the gases, but far enough apart to be moving over each other. Think about viscosity, those particles being able to roll. So we'll see these further apart particles. At that time, the energy is going into breaking, well, I shouldn't say breaking, but weakening the intermolecular forces, pulling those particles, which were tightly held together, further apart. So in order to do that, the energy has to go into affecting the intermolecular forces, meaning that energy is not being used to increase the kinetic energy, which is why we have a plateau in our temperature. The kinetic energy is not changing. Only the potential energy is changing on the plateaus. Then as we increase the heat, or as we apply heat, we increase the temperature of the water until we reach the boiling point, where we have this evaporation or boiling happening, we call it vaporization. So that happens at 100 degrees Celsius for water. And the reason this plateau is so much longer, which was pictured better in the other version, but it is much longer in real life, is because every single intermolecular force is supposed to be broken for a gas. That's actually what the definition of an ideal gas is, that there is 0 intermolecular forces. So that takes significantly more energy. Think back to your heat of fusion being 334 joules per gram and heat of vaporization 2,260 joules per gram. Much more energy required for this phase change. And so that takes more time, more energy being added. And then our gas particles are the furthest apart with the most energy. And as we increase the temperature, those particles would continue to get further apart. We think back to increased temperature, increased volume from gas laws. So you're going to just continue to see that temperature rise. So that's our kind of particle motion throughout this change. So let's focus on the phases first and the important parts there. Starting down with the solids again, those are going to be tightly packed, and a lot of times they have a crystalline or a repeating structure. Think of those nice pretty crystals that have a repeating structure. They are moving, but that movement is more of a vibration. And they have strong dominant intermolecular forces. The liquid phase, the particles are going to be further apart and they're going to be moving and flowing within the container. So the intermolecular forces would be weaker since the particles aren't as close together. And then as far as gases go, theoretically, an ideal gas has no intermolecular forces. An ideal gas would have perfectly inelastic collisions. So here's another physics idea. Those particles don't stick together at all. Bounce together, bounce apart, no effect on each other. Think of elastic collisions too from kinetic molecular theory. So fast moving, far apart, 0 forces, 0 effect on each other. So the kind of strength of the intermolecular forces definitely weakens up until there is no intermolecular forces. Strong intermolecular forces as a solid, those intermolecular forces are weakened as they become liquid and then completely broken as they become a gas. So let's look at the plateaus one by one, focusing on the lower plateau where you're going from solid to liquid. The energy is going into breaking some, weakening these intermolecular forces so that the particles can move further apart. But the larger plateau, when you go from liquid to gas, that vaporization plateau, is going to be much bigger for actually two different reasons. So I actually already mentioned the second one, that we have to break all the intermolecular bonds. But the other thing is, in order to become a gas, it also has to overcome the atmospheric pressure. So you may remember the definition for boiling, that the vapor pressure has to at least equal the atmospheric pressure. Otherwise, the gas won't be able to escape. So the vapor pressure will not overcome the atmospheric pressure. You wouldn't get any boiling. So that's another reason why we need to make sure the particles are moving fast enough, because you may also remember vapor pressure is temperature dependent. The more heat that goes into the equilibrium system, the more gas ratio, you would have more gas to liquid ratio. And so you would have more pressure coming from the gas. So you have an increase in vapor pressure until you can finally get to the point that you can overcome the atmospheric pressure. So two main reasons why that plateau is way longer. So here's a real picture, like a totally annotated picture, and we see how short the melting plateau is, and then how long the boiling or evaporation plateau would be for our heat of vaporization. It takes a lot more energy. Something else I should also note, as we're using like 0 degrees Celsius and 100 degrees Celsius, that is specifically for 1 atmosphere. Keep in mind that if you do change the pressure, you can also change the boiling point or the melting point. Think back to the vapor pressure curve. All right, guys, that's going to do it for how kinetic molecular theory and intermolecular forces affect the phase change diagram. Our next set of notes for Unit 1B will be Notes B, where we're going to talk about moles and stoichiometry. We'll see you there.